let's see.
Я все запустил уже.
А, вы запись запустили, да?
Угу.
Отлично. Okay, so well, we welcome to the Vertex operator algebra class. So well, we'll have today lecture online and the next as well. So we'll see how the situation will change after that. But please look for the updates at the web page. And also I'll be sending the email notifications. So if you have already registered, so just sending me an email, then you've got the notification already. But if you want, so probably, well, if you want to be added there, please send me an email. Okay, so also please note that the homeworks, the short problems, are uploaded to the web page, and so this will be there will be a new home problem after each class. So in particular, the first one was due for today. So if you want to send the solution, you can do it. And also I'll upload the new one today or tomorrow. Okay, so maybe any questions right now? Okay, if not, let's go on. So, well, yeah, maybe one more thing to say is that such an system, I mean the Zoom classes, they are efficient only if you participate very actively. So your questions, comments are very, very welcome, and they're very much appreciated at any point. So if you have any question, if you want somehow to discuss something, just please ask. Don't wait until the end of the lecture. So again, the more questions, the better. Okay, so let's proceed. So we have our. So let me briefly remind the. Let's see, it works. Yes. Okay. So we have two objects, so the bosonic picture and the fermionic picture. So these are two different ways how to construct the representations of the Heisenberg algebra. And recall, so we've seen the space F. Well, maybe I should start with the space V, which is the span of Vi from Z. So we have a countable dimensional vector space. So each vector from there is a finite linear combination of vectors Vi. And then, we've considered the semi-infinite search space, which is not by F. This is the direct sum of M. Okay, so each FM, yeah, maybe I should remind that we have a basis of our F as a basis of the form vi naught, vi minus 1. And in particular, we have a special vector m, which is vm, which vm minus 1, so on. Yeah. Okay, and then we've seen that the fm has a charge decomposition. Like this. And each FMG is finite dimensional, and the Q dimension 1 over Q infinity, which is okay. So this is the settings for the fermionic part, and we've seen the operators lambda n, which map the first of all v to v. So v lambda n of vk is vk minus n. So in other words, we can identify lambda n with the sum e j plus n j from z. So here the capital E's are matrix units. So this is a matrix with one unit at the jth column and j plus n row. So it takes vector j plus n and send it to j. So these are operators on V. So these operators, they induce the operators, which is denoted by Rm of lambda n. So let me denote these. These are operators on Fm. Good. Now, so well, they are induced by the Leibniz rule. The only problem is that the operator Rm of lambda 0 is ill-defined. Well, just because let's see how it works. So let's try to apply the operator Rm of lambda 0 to the vector m. So this would mean that we somehow we know that lambda 0 Vn or Vk is just Vk. And therefore, if we try to apply it to some vector, then we get infinity. So applying Rm not via Leibniz rule produces infinity. So just meaning that we have to apply lambda naught to each of the vectors vk, and well, we get 1 from each such a vk, which is of course no good. So we have to somehow renormalize. So let's put following renormalization. It says let us change the action of Eij on V as follows. So we take Eij and we replace it with Eij minus identity if I is j and less or equal than 0, and we keep it Eij otherwise. Okay. So so what does it mean? That we change the action of Eij, but we do it only for the diagonal matrix unit and only for those where these I and j, they are both non-positive. So let's see. So the claim is then, so let me put it as a lemma. So Rm of lambda naught with the renormalization as above is well defined. So let's prove it. So the claim is that the actually Rm, so yeah, maybe let me introduce a notation. So let I be collection I naught, I minus 1, I minus 2, and so on. So this is just the sequence with I naught greater than I minus 1, greater than I minus 2, and so on. Good. So this is our I. And so we denote by Vi the product Vi naught, Vi minus 1, Vi, etc. So this is our vector. So this is just for brevity. And then I claim that Rm of lambda naught applied to Vi is the Vi times the following quantity, which is the number of I in I strictly positive, minus the number of I not in I, where I is less or equal to 0. Yes, so let me say it in words that so we want to apply the renormalized lambda naught to a Verge product of the form I naught, I minus 1, I minus 2. So recall that these numbers are strictly decreasing. So the claim is that the Rm of lambda naught applied to Vi is just Vi times some constant. And this constant is actually can be easily computed. So you take the number of positive integers which are in I, and you subtract the number of non-positive integers which are not in I. So can you somebody explain why this is true?
It's true because we can because if a number is в общем, просто из определения.
Well, yes, so we see that if we take the renormalized lambda naught and we apply it to so Vk or Vi, then so this is renormalized. Then this is going to be either Vi, yes, if I is positive, right? Or 0 if I is less or equal than 0. Correct? Because we've subtracted the identity for I equal j, and both numbers being non-positive. So for positive, nothing changes, but for non-positive, we are getting 0. Therefore, if we're applying the lambda naught to vi, then the result is so the result is either so let's see. So we take Rm of naught and apply it to say so we see that there are several places where we can apply and get the 1. Yes, and so otherwise we're getting 0. Yes, because the so let's see that yeah, maybe I should this is wrong. Yes. So I mean, so this we have recall that this lambda 0, yes, becomes lambda 0 minus identity. Yeah. Okay. So is it clear, or shall we discuss it in more details?
Can you explain it?
Okay. So Sasha, can you give some details here?
Ну, в смысле, ну вот, значит, мы действуем. Я не совсем понимаю, что непонятно. То есть.
Okay, let's work
I mean,
out.
after we change the EII, the lambda 0 changes to that, yes?
Ну да. Ну, то есть у нас получается, что лямбда 0, оно, значит...
So let me write it. Yeah, Sasha.
Вот если мы действуем, ну, если мы лямбда 0 применяем кому-то из отрицательных мод, ну, то есть из v при и меньше нуля, то тогда оно сейчас. Тогда оно не действует. Сейчас, правильно сказать.
So this is the formula, right? So this is the formula how Rm of lambda naught acts, right? So we have to apply this formula to our vector, okay? So so Rm of lambda naught applied to Vi equals to some EII positive, some I less or equal than 0.
Можно так сказать, что вот давайте посмотрим сначала, как действует на вакуумном векторе.
Oh, we can just write it as like this. So please have a look. Yeah. Okay. So we have several terms, and then so let's look separately at each term. Yeah. So so this equals to Vi if I in I, and equals 0 if I not in I, right? And these terms, this term equals 0 if I in I, yeah, because we subtract identity, and equals to minus vi if I not enough. Okay, so therefore we are, in order to compute the number of VI's showing up in this formula, we have to see how many, so totally we get, so this equals VI times the number of I greater than 0 and I in I. So this comes from here. And minus the number of I not in I and I less or equal. Okay. So an example, yeah, maybe I should write it as not an example, as a corollary. The corollary says that if we take Rm of lambda naught and apply it to, yeah, so just so let me write it equals to m times identity on Fn. Yeah, just because by definition, so maybe we didn't say it like this last time, but let me say it now that the charge M Verge product so on. Yes, they consist exactly of those VI such that the number I in I greater than 0 minus I not in I less or equal than 0 equals M. Yeah, so it's clear that for example, the vector M sits in Fm by the very definition. Yes, so it's either if M is non-negative or positive, then we get the first term, and then if negative, we get the second term. Yes. And yes, sure.
А если мы могли вот этого все не делать, а просто сразу там зафиксировать, ну так глупо, но могли. Почему нет? Взять теорему от лямбда.
Sorry. Sasha, can you repeat it?
Сейчас, меня не слышно?
I can hear you now. Yes.
Просто что-то кто-то говорил еще. Вот, я говорю, что могли бы просто наивно сделать по-глупому, что значит просто вот эту формулу, которая у нас в следствии, взять за определение действия лямбда 0.
Yes, so you are absolutely right.
Или взять какие-то другие числа.
Yeah, we could have taken this formula just as a definition. You are absolutely right. But just yeah.
Ну, вопрос в том, какой, как бы, не знаю, какую, ну, видимо, ну, если так сделать, то в дальнейшем, видимо, нужно будет какие-то неочевидные вещи доказывать. Вот вопрос, почему сейчас. Почему логично сделать именно...
Well, the reason why we are taking...
Ну ладно, не знаю. Вопрос в том, что если так сделаем, то как бы эти процессы согласованы.
So you see, we've defined the action of the lambda k. So let's see.
Probably because you want to get a representation of some algebra.
So you see, we have this definition, and the definition is very general, yeah. So it doesn't depend on n, yeah. So it works for any lambda. So in particular, well, we should have a reason why we want to have a separate definition for lambda 0. Yeah, we don't have such a reason so far, but since we have a problem with the action of on the semi-infinite Verge space, so this is the reason. And then we start trying to renormalize it to make the definition rigorous, and this is how it works. Of course, we could have defined lambda 0 separately from the very beginning, but then we need a reason for that. Okay?
Okay.
Mm-hmm. And so there was a question by Andrei, but what do you mean the definition in terms of stabilization?
That we have I minus k is equal to m minus k.
You mean that, let's see, I minus k equals to m minus k, right?
Yes.
Okay.
It's our definition, yes? Or
it is a definition.
I missed something.
Yes, yes. So you're asking
But,
why this is equivalent to this formula, right? So this is the question, right?
Yes.
Mm-hmm. So again, can somebody explain?
Yes.
Timur or Sasha or somebody else?
You can check
No.
it for vacuum vector and then show that if you will change this vacuum vector to other vectors, then both definitions will not change.
Yes, so indeed, so we could have started with IVM, Verge VM minus 1, Verge VM minus 2, and so on. So this is the charge M vector, and then we somehow take several vectors here, and then move them somewhere to the left. And these are actually all the charge M vectors. So now clearly such a procedure is compatible with this definition. So we do not change a tail. Yeah, maybe I should have written here that for k large enough. Yeah, so this does not have to be true for all k, but only for large enough k. So how do we obtain such vectors? So we take the vacuum vector VVM, and then we move several places to the left. So then clearly this is compatible with the second definition, and then we can see what happens with the first definition. I mean, with this one. You just need to check that the problems do not occur, and this is clear because either you move a negative vector to the positive, or you just move positive to the positive. I mean, there's no way how you can change such a difference moving moving some concrete number of vectors to the left. Andrei, does this make sense?
Okay, so explicitly we have propositions that if we have some vector with which defined as I minus k is equal to m minus k, we can obtain it by some permutation from vacuum. Yes.
Well, it's not a permutation; it's some change.
Yes, like change.
Because we do change vectors, we're not only permuting them, yeah, but shifting by some shift, yes?
Yes.
Vector. And then you just check that after the shift, nothing.
Yes,
changes.
yes. Okay, thank you.
Welcome. So any other questions so far? Okay. Good. So now let's go further. So now let me put forward the following proposition. So the operators are m of lambda k with renormalized lambda naught define the action of the Heisenberg algebra on effect. And and let me also say that Fm is isomorphic to pi m, which is the Fock model. Yeah, so recall that we've seen the Heisenberg algebra last time, and it's Fock module pi m, where m is the, so recall that Heisenberg algebra is the span of H I, and center. Well, let me do it by one. This. Okay, and then the Fock modules are pi lambda. So H naught, yeah, pi lambda with highest weight vector. Lambda. Such that H naught lambda is lambda times. So, well, it was the homework problem that Rm of lambda n, Rm of lambda m, or lambda k is delta n plus k0 times m. Okay. So that's it. And so.
Sorry, is it m or is it n?
Where?
It's m.
Oh, sorry. Thank you. Like this, right?
Yeah.
So correct now, right? Okay, so this is the formula which matches with the commutator relation for the Heisenberg algebra. So we indeed have an action of the Heisenberg algebra. The renormalization is now not that important because we are only changing the lambda 0, and so Rm of, so let me say it in words. So in particular, the renormalized Rm of lambda 0 commutes with everything. Okay. So this is the conclusion, and we only need to check that the so the isomorphism so we are left to check the isomorphism for M as H modules. Okay. So this is the goal, and actually we know this because so we know that Rm of lambda naught applied to M is M times M, and we know that Rm of lambda positive applied to M is 0. And we also know that the finally the vectors lambda minus J1 Js applied to M are linearly independent. So actually we've seen this argument last time when saying that if we have an action of a Heisenberg algebra, yes, with the properties that the H naught somehow scales the high state vector and the positive modes they kill it, then such vectors are linearly independent. You just apply the differentiations, yes, and you go on. Okay. So do we need to discuss this in more details, or is this clear?
Don't we need to check that vectors of kind lambda minus J1 and so on acting on M should generate the whole module?
Yes, but indeed, in principle, yes, but recall that we've seen last time that the Q dimension of Fm equals to the Q dimension of phi M equals 1 over Q infinity. And therefore, the sizes of the spaces are equal. Okay.
Okay. And can you please repeat why are they independent? I missed something.
Yes. So maybe somebody else can say this.
Because of the Schur-Lemma. So we have map from Fock module to our space, and as soon as Fock module is irreducible, it is injective. The map is injective.
Yeah, so well, you can see that if we have a so the Fock module is irreducible, and so this actually can be seen easily in the same way as proving that these are linearly independent. Just if you have an action of the Heisenberg algebra without no further conditions, then these such vectors are indeed linearly independent. Okay. Good. So let's go further. So we have, let me see. So we have our F, direct sum of Fm, and it makes sense. To consider the corresponding bosonic space B, which is the, yeah, maybe I should have also recalled. So each phi m is identified with a polynomial ring in infinite number of variables, namely, we take, so let me see the convention. So, sorry, just not to mix. Yes, so we identify, Hj with d over dxj for j positive, and h minus j with j fj if j is still positive. Yes, so with such an identification and the I-state vector of phi m is identified with the unit okay. So this is the identification. So recall that phi m actually is equal to c of h minus 1, h minus 2, and so on, with well, some question. So please don't write, but please ask if you have a possibility. Daniel, you have some question? Or you can write it in the chat. No, so probably the question was about x naught, but the x naught corresponds to h0, which acts as a constant operator, so we don't need it. Yes. So we don't need x0 because so it corresponds to h0, and this h0 acts as a constant, so we don't need it to generate the representation space. Okay, so this is our convention, and therefore so you can see that once again each phi m is identified with this polynomial space, and now we have a f, which is the direct sum of fm, and this is somehow identified with the direct sum of phi m. Okay, so that's it. And now so let me write at pi m. Sorry. Oops. So can you see my screen?
Yes.
Okay, so let us identify. Sorry. Oh, okay. So pi m we identify with z to the m, c of x1, x2, and so on. So this just to distinguish between different Fock modules. And then the direct sum of pi m is identified with the polynomial in Z plus minus 1, 1. And so this is identified with the Fock space. And so this is the bosonic space we denote by notation. So B is going to be this C of Z plus minus 1. So this is our B, and this is the direct sum of Bm, where Bm actually Z to the m times this ring of polynomials. So, well, the logic now is that we have some structures on the fermionic space, and then we want to translate it to the corresponding structures on the fermionic space, on the bosonic space, and then just see how it works. So because this bosonic space is nothing but the polynomial rings, and therefore we can look for some polynomials or some interesting examples, and so on and so forth. So then what is the structure we are looking for? The structure is as follows. Let's see. So consider the operators vi hat. So the operators on F defined as follows. So if we take vi hat applied to vi, there's nothing but vi verge v sub I. And if we take vi hat star applied to the same vector, this, then this is equal to delta, well, it's equals to 0 if I is not an I, and it equals to minus 1 to the k times, so if I equals I minus k, then you just take v I without I minus k. Okay, so it's kind of deleting a vector if it is there, and if it is not there, then we just get 0. Okay, so we have these two operators. So the first is kind of verging operator, and this is the contracting operator. So these are two operators acting on our vector space. And now the question is, what do they form? So what is the algebra they form? And this is the so-called Clifford algebra. So let me put it as a lemma. So the operators vi hat and vi hat star satisfy the Clifford algebra relations. And these relations are as follows. So you take vi hat, take Vj hat, and the supercommutator, so meaning that you take in one order and then sum up with the product in another order, equals to 0, and then Vi at star plus is also 0, and then finally Vi at star plus is delta I. So this everywhere we have anti-commutators, right? So the reason is that because we are acting on the Vertex space. So do we have to discuss this in more details, or these relations are familiar? So please, yeah, let me write it. So the definition of, oops, sorry. So AB plus is AB plus BA. So this is the so-called anti-commutator. So please raise your hand or write in chat if you want to discuss these relations in more details. So otherwise we'll go further. So in principle, it's very straightforward to check all those relations, but with the definition given here. But if somebody never seen this or you want to discuss, please let me know. Okay, so if not, let's go further. So let me add the remark. So the space F is space F is spin representation for the Clifford algebra. Okay. So well, this means that if we take, so more precisely, so the you take 0, so the whole space. So maybe let me denote it by CL. This is the Clifford algebra. So this is the associative algebra generated by Vi hat Vj hat star with such relations. Yeah. So meaning that F is obtained by applying the Clifford algebra to the vacuum vector 0, and we know that Vi hat vector 0 is 0 if I is less or equal than 0, and Vi star 0 is 0 if I is positive. So there's a part killing the vector and another part generating the whole space from the vector. So that's it. So these are our operators, and then so any questions about this Clifford algebra action? Okay, so one more remark is that the operators Vi hat, they act from Fm to where?
Fm plus 1.
Yes. They increase the charge, and Vi star, they act in opposite direction. So this is the obvious remark, yeah, because VI they verge and VI star they contract. Very good. Now, how do we proceed? So the question is, how do we translate the action of the I hat I star to B polynomial space? Okay. So how do we translate? So what are going to be the corresponding operators on the B side, on the bosonic side? And for that, we need some more computation. So let me add this as a lemma. Saying that we take Rm of lambda k, and then we take, or rather, let me put a j here. It's going to be vk minus j. And if we take Rm of j and vk star, then it's going to be minus vk plus j. So like this. So this is the claim, and actually the proof is rather simple. So how do we show this? So what is the Rm of lambda j equals to the sum over A from Z, V at A with head star A plus J. So do you agree with such a formula?
If j is not zero.
Sorry?
If j is not zero.
Yes, J is not zero. That's right. Okay, so this is the sum, and now
do lambda zero, I mean the expressions above, they are true for j equal to 0?
Yes, that's true for j equals to 0, but the proof should be worked out separately. But actually, how to say? No, I'm sorry. For lambda 0, what is Rm of lambda 0?
Число просто, поэтому оно коммутирует.
See?
No, why?
So-
нет. Нет,
Let's
она
see.
меняет заряд, поэтому... Да.
So are these formulas correct for lambda 0 or they're not?
No. It's this bilinear combination is the same as matrix identity. And we should modify the matrix identity in the same way as above, like to subtract ID in some for I.
ID коммутирует.
Rm of lambda naught, they already renormalized, yes? So we've defined them in a rigorous way. So let's always assume that Rm of lambda naught is exactly the renormalized quantity, yes? So it's well defined.
Ну, дело в том, что RM от лямбда 0, оно сдвинуто на какую-то, в общем, это ID, оно... Сейчас.
Коммутатор
Я не так уверен, но в основном она просто коммутирует.
So let's see.
Charges are different, so it should be 1 and -1, I think.
So let's do an example.
Lambda 0 will act with different constants, so I don't think it's that true.
So do you vote this is true or not?
Это правда,
Yes.
потому что как раз вот до того, как подействовать, давайте так вот, значит, RM от лямбда 0, оно действует, сейчас только у нас, как вот, подождите, значит, RM, наверное, не очень корректная запись, потому что у нас M, оно как бы меняется, то есть один раз
You
RM, а
are
другой
right.
раз RM.
Yes, this is a good point. So I should erase M everywhere. So because indeed, so this is an action on F, but not on M, separately on FM. So we somehow have this R action, which combines all the, so maybe I should write this also. So remark, R of lambda k is an operator on F, direct sum of Fm. So this is the combination of all R, so it's the collection of all Rm of lambda k for all M.
Вот.
Мгм.
И можно я попробую объяснить, почему для лямбда 0 все работает. It is true because if we, мы можем сначала подействовать r лямбда 0 на, ну хорошо, давайте в таком порядке. Сначала, значит, сейчас, только я забыл, выкинули или добавили сначала. Ну, в общем, в одном случае сначала выкинули. Сейчас, я забыл, какой
Let us
выкидывали.
write it explicitly. Yes? So if we apply this
значит,
VI for VI in FM, yes, as Sasha is saying, so we can first apply the VK hat to VI and get to M plus 1. Yes, Fm plus 1. And then we apply R of lambda naught, so we're getting M plus 1 from the first summand. And then we subtract M, and this is applied to VI verge VI. Oh, VK verge. So this is indeed true, and for the second, it's true as well. So we only need to compute the non-zero term. And then for this non-zero term, this is rather simple. So we want to look at VA plus J star, and we multiply it, say, with VK. And by the very definition, this is minus VA, VK, VA plus J star, plus delta A plus J K times VA. And the latter is just VK, VA, VA plus J star, plus delta A plus J K. Okay, so then the commutator VA and VA plus J star and VK hat turns out to be just one single V corresponding to A plus J equal K. So this means that A is K minus J. And actually, this is what we want. And similarly for the commutator with the contraction, So it works. So similarly. With the contraction operator. Okay. So this is already something, and we want to somehow, as I said, we want to construct the corresponding operators on the bosonic side. And in order to do this, let us introduce, so consider generating functions. And these are x of u, x star of u. Good. So this x of u is by definition the sum u to the j v j hat, and this is the sum u to the j. Let's see. Yes. Let me put v minus j here. Okay, so these are the generating series for verging and contracting operators. And let me put forward the following lemma, saying that R of lambda k x of u is u to the k x of u. And so we also need R of k with f star of u. And this should be minus u to the minus k x of u. So let me see if I wrote it in correct way. Yes, but this should be plus here. So the only difference is that we have minus in one case and we don't have it in the second case.
I think we should have star on in the second row.
Absolutely, thank you. Okay, and so actually there's more or less nothing to prove. For example, for the second thing, we take R of lambda k, and we take sum u to the j, v minus j star hat. And the result is sum u to the j, and the commutator of R of lambda k with this guy is minus v hat minus j minus k. Right? So this comes from the formula in the lemma here. So we sum k plus j and we add minus. Oh, that should be plus here, right? And this equals to the sum minus goes out, and then u to j minus k v minus j plus k add star, and then we have to multiply it to u to the k. Does this make sense? Okay. So this is it. So now we have two generating functions. Now our question is how to write down these generating functions on the B side. Okay. So this is the question. Good. So now how to answer? this question. So again, one more piece of notation. So gamma notation. So let us write sigma for the identification of f and b. So in particular, sigma fm identifies it with bm, which is the just polynomials. So recall that this is e to the m times c of xi, I is positive. Okay, and so we write gamma of u to be the following thing. So we take first sigma inverse, then x of u, and then sigma. So this is the operator, the generating function of operators on B, because we first go from B to F, and then we do something on F, and then from F we return back to B. So this generating function gamma of u is now the series with coefficients being operators on B. Okay.
I have a question. Why did we apply sigma minus 1 to the generating function, but not to vi and vi star themselves?
So you see, this sigma is an operator from F to B. Okay. Yes. So in particular, so what is this gamma of u? So gamma of u is a series in U, and this series consists of operators acting on B. So do you agree? So, well, in other words, you can take a vector from B, apply gamma of u, and the result is going to be a series with coefficients being vectors in B. Okay. And also we define similarly gamma star of u, which is sigma star of u, like this. Good, very good. So this is our definition. Now, so we want to compute this gamma of u and gamma of u star of u, and these are now operators on polynomials. So here is the following lemma, saying that if we take d over dxj, commute it with gamma of u, then the result is going to be u to the j gamma of u. And if we apply j at j to gamma of u, so then the result is going to be u to the minus j gamma of u. And similarly, we have for gamma star. This is equal to minus u to the j gamma star of u. And this equals to minus u to the minus j like this. So can you tell me how to prove this? Why is this is true?
It is because sigma is isomorphism of the models, and
Yes, exactly.
we know that no, we know the same relations in for x, and they are, ну, в общем, они сохраняются, когда мы, ну, d по dx и gxg это, собственно, наши, ну, гейзенберговские эти действия. Вот, и мы знаем, что они сохраняются при гомоморфизме.
So indeed, so we know that sigma is an isomorphism of H modules. So this is the just by construction. And also we know that these operators d over dxj and j times xj, these are exactly the operators corresponding to the Heisenberg algebra. Yes, so recall that ij, so maybe I should, so for j greater than 0, so R of lambda j is identified with hj, and this is identified with d over dxj, and also R of lambda minus j identified with j h minus j. Oops, sorry. And this is identified with jxj. Okay, so this is just by our construction, and now we simply apply. So now we apply the commutation relations of the form Rm of lambda, oops, sorry, R of lambda k x of u equals to u to the k x of u. Yes, just by what we've just seen, and similarly for R of k, R of minus. Okay, so then these relations, which we see in the lemma, they are just reformulation, rewriting what we already have. Okay. So now the theorem comes. It says how to solve these relations. The solutions is as follows. So if we take gamma of u, and we restrict it to b of m, then the result can be written in a very explicit form. And this is the first probably historical appearance of the vertex operators. So this is u to m plus 1, c. And then the product of two exponents, x of sum u to the j, xj, times exponent sum j positive with a minus, and u to, sorry, times minus u minus j over j times d over j. So this is for gamma of u, and now for gamma star of u, this is u to minus m, z inverse, and c still x of minus some uj fj times x of j positive, u minus j over j over dx. So let's look at these formulas. So actually the proof is going to be your homework, but let's at least see what's written here. So you remember that Bm is just a polynomial ring in variables x, and therefore we want to apply some operator acting on the x variables. So in both expressions, you have u to some power and z or z inverse on the left, so which produces you a shift from Bm to Bm plus 1 or from Bm to Bm minus 1, so as it should be. You also have some exponents. So exponent, of course, is an infinite series, but let's see how this infinite series work. So the right terms, for example, here. So you have an exponent of the derivatives. So therefore, if you apply it to some given polynomial, only finite number of terms survive. Okay, and therefore this is a polynomial in U with some coefficients being polynomials also. So in the second identity, it's Z inverse because we want to move from Bm to B. Oops. So let me write it. So it's Z minus 1. So because we want to move from Bm to Bm minus 1. So in the second, so this is the, say, this exponent. So it produces you some polynomial in U with some coefficients being polynomials in X's. And then you multiply it with the series, which produces you series in U, but it's fine. And similarly, in the second equality, this is also well defined. So you see the products, the two exponents. One is written in terms of positive powers of U, and another in terms of negative powers of U. But once again, this does not produce infinite sums, because if you apply it to the concrete polynomial, the second factor actually is finite. So is it clear what is written here?
Yeah.
Okay. So well, there is a question in the chart about the product. You see, so you can't multiply them in a trivial way because the xj and d over dxj, they don't commute. So therefore, it's important in what order you are writing. So you can't move one exponent via the other one. So of course, there are some formulas for that, but there is a kind of, it has to be done carefully. So the product of gamma of U and gamma star of U cannot be written in this simple form because of the two exponents. I mean, so these two exponents, they do not commute. The operators do not commute. So any further questions? Okay, so if not, let me start sharing. And so I'll upload the home problem to the web page. So if there's no further questions, then goodbye and see you next week, also in Zoom. Please check the updates on the web page.
Thank you and goodbye.
Thank you. Goodbye.
Thank you.
Thank you.